Okay, so let us start our discussion on quantum theory of radiation in this video. So the last video, I mean the few last videos that we had our discussion on classical theory of radiations, right? So where people like Wien, Lord Rayleigh, James Deans were trying to explain the experimental observation that they had, in the experimental observation the people had obtained in the black body spectrum, right, where the variation of energy density that was seen, that it peaks at certain range of or certain value of wavelength it peaks, and then in either side it decays down, right? So there was a blackbody spectrum which was obtained experimentally by in the experiment performed by Larmor and Prinshim, right? Then this Lord Rayleigh and Wien, the Rayleigh-Jeans law and the Wien distribution law had attempted to explain these experimental observations, but unfortunately Wien was his law was successful in explaining the blackbody spectrum for shorter wavelength at low temperature, whereas the Rayleigh-Jeans law was successful in explaining the blackbody spectrum for longer wavelengths at higher temperature. But none of these laws could explain the entire blackbody spectrum, right? So then around this 1900, the beginning of the 20th century, this Max Planck had come up with a revolutionary idea of where he introduced that, the exchange of energy within that black body, in the enclosure where this black body radiations are present, happens only through in quanta of energy, in some energy packets, meaning this the radiation or the black body which emits or absorbs the radiation, this exchange of energy process happens only through quantas of energy, and which he later on it was termed as photon. Okay, so and each photon carries a discrete amount of energy or discrete values of energy, which was the Planck termed as h nu. H is a Planck constant, where nu is the frequency of that radiation. And then he gave the idea that this exchange process, the absorption or the emission process, happens only in discrete quantas of this h nu. Okay, so that was the idea. Okay, so now this is the new unit which we are trying to start here. Okay, so and this comes under this quantum theory of radiation, or colloquially it is known as the Planck's theory of radiation as well. Okay, and this was the beginning of this quantum physics that we all know today. Okay, so in this video we'll discuss about this Planck's law of blackbody radiation, then the hypothesis or the assumptions made by the Planck's theory, whatever assumptions he made to come up with the expression that could explain this blackbody spectrum, the experimental observations of the blackbody radiation, and then eventually we will try to derive this Planck's law. Okay, so in similar to Rayleigh-Jeans law, what they considered it an enclosure filled with radiation in thermal equilibrium. Similar to that, the Planck had also assumed a similar cubical cavity. So the ideas will be borrowed from that theory, some of part, but instead of having the classical oscillator, where in the Rayleigh-Jeans law this classical oscillator or the radiator or resonator, which could exchange the energy in any values of there is no, it could exchange any amount of energy, right, during this absorption or emission process. But on the other hand, this Planck assumed that these are some kind of the classical so these are some quantum oscillators. Okay, this quantum harmonic oscillators where the exchange of energy happens only in this discrete quantas of energy, okay, which you will see in this our study that we will go through in this video. Okay, so Planck, as I said, came up with this empirical formula which could, which had fitted these experimental observations of the Larmor and Pynchon experiment, right? For the black body spectrum which they had obtained experimentally. So in terms of frequency, so these laws we will try to derive. Okay, so they came up with this. Okay, and in terms of wavelength, this is this. Okay, so if you remember the expressions for Rayleigh-Jeans and Wien's law, you will see that there is this exponential term had come up here. Okay, so we'll try to derive this law. So yes, so now let's try to look at the hypothesis or the assumptions that, or the quantum postulates which Planck's theory had started with. Okay, first of all, it assumed that this black body radiation chamber is filled with not only the radiation but with simple harmonic oscillators of molecular dimension. As I said, these are the simple harmonic oscillators. Okay, so these are, as you can see, these are quantum oscillators. Okay, and these are known as Planck oscillators or resonators. So this is the first assumption. So that this chamber, this cubical cavity which we had discussed in the Rayleigh-Jeans law, that this not only filled with radiation but it also has got this simple harmonic oscillators, right? And these oscillators can vibrate with all possible frequencies. Okay, so it can vibrate in all possible frequency, okay, or can emit all possible wavelength, or it can even absorb all possible wavelength. Okay, but this emission and absorption process, okay, it happens only in the forms of packets of quantas of energy which is known as photons, and each photon has got energy h nu, where h is a Planck constant, okay, and then nu is the frequency of the oscillator. So these are the four very important postulates which we need to remember. Okay, and based on this we'll try to now derive this Planck's law of black body radiation. Okay, so we'll first of all we'll make some, as any theory starts with some kind of assumptions. Okay, so we had all these four assumptions, and then let us consider that there are n number of total Planck's oscillators in the cavity that we are considering. Okay, so and let's say total energy be E inside that black body radiation enclosure. Okay, so the average energy of these oscillators will be E by capital E by N. So E bar is your average energy. Now, okay, now let us consider, as you have seen, that these oscillators can oscillate in any like all possible frequencies. So now let's talk about this. Let's say there are n0, n1, n2, n3, n4 number of oscillators which are present, okay, within this enclosure, and having energy, let's say 0. Meaning, see here you will see that some ideas of classical theory also being used. Okay, not that entirely this quantum mechanics, okay, or quantum theory. Okay, so this, let's say there are n0 number of oscillators which are having 0 energy, n1 number of oscillators which has got energy, this script E. Okay, similarly this n2 are the number of oscillators which are having 2E. Similarly n3, n4, n5, if I take in general some nq number of oscillators have got energy QE. Okay, this is like generalized version. Okay, now using this Maxwell-Boltzmann distribution law, this is a classical stuff that we have studied in our earlier videos, right? So the number of oscillators having energy EQ, like distribution of energy, now we can write in terms of this the having, I mean n0, you will see what I am talking about. So this NQ is the number of oscillators are having energy QE. Okay, this is given by this particular expression, and not e to the power minus q E script E, okay. So then K is a Boltzmann constant and T is a temperature, right? So this we have studied in our Maxwell-Boltzmann distribution, right? Similarly, we can have this N1 will be given by this expression N1 equal to N0 minus E by KT. Similarly, N2, N3, and I can write N4, N5, and like this, okay. So if I have to write in general one, it is given like this, okay. So if I have to simply write one like 5, then it will be N0 e to the power 5e by KT, okay. All right. So, and I assume that, as I said here, there are total of n these Planck's oscillators. So you can, n will be equal to n1 plus n2 n3 all the way. How many of our Planck's oscillators are present? You can sum of them. It should give you the total number. Okay. Then simply substitute for n1, n2, n3. Okay. In general, and you can write the in general term also nq, then keep on going the term. Okay. So substituting for n1, I'll get this. Okay. N2, n3, all this. Now I can take n not common out of this expression, and I'll remain with this term in bracket. Okay. Now here what you have to do, let's let us assume that x is equal to e to the power epsilon kt. Okay. So this expression in the bracket will become 1 plus x square plus x cube, isn't it? Then similarly it will keep going, right? So this is what? This is geometric progression, right? And here it is x. From here you can see that the magnitude of x is what? Is less than 1. And this is geometric progression, GP. Okay, so and then if you know from your basic mathematics, right, the sum of this expression will be given by what? First term here is 1 by 1 minus this x. So x is what here? So sum of this infinite sum of this series will be given by this, right? So which will be equal to 1 by 1 minus x is what? E to the power e by kt. Okay, so n naught was here, so this is what it is given here. Okay, all right. Having obtained this expression for n, which is n equal to n naught by 1 minus e to the power minus e by kt. Now let's go back to this total energy. Okay, so total energy, we know that there are n naught number of oscillators having 0 energy, n1 having e and energy E, similarly n2 having energy 2e, n3 having energy 3e. Okay, so the total energy of the system will be 0 into actually n naught, okay, which will eventually give you 0, e into n1 twice e into n2. Similarly you can keep going by following the trend. Okay, so then substitute for n1 again. Okay, n1 we know this n naught e to the power minus e by kt. Similarly for n2, n3, n4 you can keep on substituting. Okay, now I can take common, right, n naught e to the power e by kt. This is script e. So what I mean by here, okay, and I'll remain with this term in bracket. Now again now let's so whatever x we have taken, let's keep same x. So let's again x is equal to e to the power minus, let's say, kt. Okay, so now this term in the expression in this bracket, within the bracket, will be 1 plus twice x plus thrice x square, similarly 4x cube. Okay, it will keep going like this. This term is, it is a binomial expansion of 1 minus, so since I have used x here, x, it will be minus 2. Okay, so this is a binomial expansion of this 1 minus x to the power minus 2. Okay, those who are not familiar with this, please go back and check, revise your concept on binomial expansion. Okay, so, and if I substitute back here x, what we assumed here, so I will get back this, right, this minus 2, so it will come into denominator. So then now I have got expression for total energy, right? So I have got expression for total energy now. Total energy is given by this particular expression. Alright. So we are trying to calculate this average energy. So E I have got, N I have got. So the total, the average energy of the oscillator is given by this. So then I have just substitute the expression for E and then substitute for divided by N. So the substitute for N, so it will be like this, N naught by, so it will be N naught, so N naught will remain in the denominator and then the other expression will go on top. Okay, so here as you can see from this, your N naught will get cancelled and the one expression, this one, so this 2 will go off. Okay, so I will remain with whatever this E into e to the power exponential to the power minus E by kt, then 1 minus exponential E, minus script E by kt. Okay, and later on what I can multiply on numerator and denominator by e to the power kt, down also e to the power kt, so then I will remain with this expression. Okay, but we know that as our assumption, which we, or according to the quantum postulates that we have seen in the one of these beginning slides, that script E is the energy of a photon, right, which is h nu. So after substituting, we got the average energy of the system, okay, or the average energy of each oscillator, okay, which is h nu by e to the power h nu by kt minus 1. Okay, now this is the idea, or this is the expression which we'll borrow from the earlier studies. Okay, this number of oscillators per unit volume in the frequency range. This, see, in earlier videos while calculating or while deriving this Planck's law, while deriving Rayleigh's law, we had calculated the number of modes of vibration per unit volume in the frequency range. Okay, so now if we associate for each mode one oscillator, I can use the same expression here. Okay, so the number of oscillators per unit volume in the frequency range nu and nu plus d nu, this we are already familiar with, right? So it is given by this. So now I know the average energy. Okay, so in earlier case what happened, we had used the classical mechanics. After Rayleigh's, after calculating this number of modes or number of oscillators per unit volume, we had multiplied by the average energy to calculate the energy distribution or the energy density, right? So there we have taken average energy to be kT, but here because we assume this to be quantum oscillators, so we had calculated our expression for average energy a little differently. Okay, so if I multiply, so after getting this expression for number of oscillators per unit volume in the frequency range that we have considered, so the energy density can be written as simply just so we already have number of oscillators per unit volume, so multiply by the average energy will give you energy density, right? Simply you have to multiply by this expression with meaning the n nu d nu, I have to multiply by average energy expression. So if I do that, I just simply substitute the expression for average energy that we had obtained here. Alright, so if you do that, you know, this h nu, then 8 pi nu is there, so this nu there, it will become cube, so you will get this expression. Okay, so this is the expression for Planck's law of blackbody radiation in terms of frequency. Okay, so and this is the expression which fits well for this all the experimental data that they have obtained for blackbody spectrum. Okay, and in terms of wavelength, same expression can be derived. We know, so this we have done for Rayleigh's law. In the same line we have to continue our mathematics. So nu is equal to c by lambda and d nu is given by this. Okay, d nu is given by this. So then it's simply you have to make the substitution for nu and d nu, and after doing this much of algebra, you will end up getting this. So this is the expression for Planck's law of blackbody radiation in terms of wavelength. And as I told you, this expression fits this experimental data of black body spectrum really well. Okay, and which gives you that, you know, the shift in the meaning the lambda m, the wavelength corresponding maximum energy radiation, meaning that shift towards the left as we increase the temperature. Okay, so all these characteristics that we have discussed in the previous video, it is given here by this particular expression. That's why because this idea clicked, right, and it was, that's where a new dimension of physics have when it come into the discussion, right? Because just by fact that the exchange of energy process happens in quantas of energy, or in some discrete way that this absorption or emission happens, so the exchange of matter and the radiation, the energy exchange process happens through some discrete quantas of energy. Because of that idea, this entire thing fits well. I mean, the experimental data was explained successfully by this law. Okay, so we will stop at this point, then we'll have some more discussion on quantum theory of radiation in the next video. Okay.